So we will start with this topic, Kirchhoff law. Now, Kirchhoff law is a very important concept and very important topic as such. And you will come across a lot of students who have doubt in Kirchhoff law. That means they will have a lot of doubt over solving problems involving Kirchhoff law. Law in itself is very simple. Law is not complex. But when you end up solving a numerical, there are steps that has to be followed. If you don't follow that step, you will never get it through. So first understand the basic and then we will move towards solving a numerical. So Kirchhoff law mein first is what is an electrical network? These are simple definitional stuff. The term electrical network is used for a complicated system of electrical conductors. Very simple. If you have many conductors arranged in some or the other way, like series or parallel or mixed up series parallels, and you have different cells that are arranged in series and parallels. You have done all these topics before. So they are all called electric network. Then there's something called junction. Now, what is a junction? Any point in the electric circuit where two or more conductors are joined together is called a junction. That means if you have like something like this, if you have a current which is coming to a point and another current is also coming to the same point, that means this will be a junction. Okay, this will be a junction. Again, if this junction goes and these two current again divide further, I mean they will become like this, I1 I2 again. So this is also a junction then. Okay, this is also a junction. This is also a junction. This is also a junction. Very simple. Then loop or mesh. Now what is a loop or mesh? Any closed conducting path in a electric network is a loop or mesh. So what does this mean? Now if I draw a simple resistance and a cell like this, so this is one loop. So loop means starting from this point, conducting path and coming back to this point. This is one loop. But let's say if I have a network like this, then how many loops are there? So you will think that there are two loops, loop 1 and loop 2. But no, there are actually three loops, 1, 2, and the outer one is also considered as a loop. Okay, the outer one is also considered as a loop. So there are effectively three loops. If if I draw a circuit like this, just hold on, let's say a circuit like this. Now how many loops are there? So again you can say that this is one loop, this is two loop, and the one which is on the outer, this is also the third loop. So there are three loops effectively. Okay, there can be 4 loop, 5 loop. Some complex circuit may have 6 or 7 loop as well. There are questions in NCERT where the number of loops can be 5 as well. Okay, very important to identify loop. For example, let's say this circuit, look here. Now you don't need to think about the current resistance and everything, only focus upon the number of loop possible. So here I can say that this is one of the loop. Again, this is one of the loop. Then I can also have this as one of the loop, 3. Then this can also be a loop, 4. But then I can also have this as a loop, 5, and also this as a loop, 6. So you can see how many loops we can make. Okay, how many loops we can make in this kind of circuit. So I hope everybody understood what is a loop or a mesh in an electric network. Okay, this is clear. And then a branch. So what is a branch? A branch is very simple. A branch is a part of a network that lies between two junctions. So for example, this is a branch. In this case, you can see this is a branch because this is a junction and this is also a junction. So this is a branch. Okay, this one. Very simple. Now let's move toward understanding the Kirchhoff law. So the first Kirchhoff law, or the first law, is also called the junction rule. Kirchhoff first law is also called junction rule, or it is also called current law. Okay, this is the the Kirchhoff first law, or it's also called the junction rule. And in an electric circuit, the algebraic sum of the current at any junction is zero. Okay, the sum of the current entering the junction is equal to the sum of the current leaving the junction. Very simple. That means if you have a, let's say, a 3 ampere current coming towards this point and a 2 ampere current towards this point, so there are total 5 ampere current that has come towards this point. That means from this point 5 ampere current must also leave. Okay, so that the algebraic sum here at this junction must be 0. Okay, now this is very simple, and you can have certain sign convention here as well, but the sign convention is not very important. If you look into different books, you will find that these sign conventions are also stated. Sign convention for applying the junction rule, the current of flowing towards the junctions are taken as positive, and the flowing away from the junction are taken as negative. This is not a universal. That means many books will use this convention. Some of the books will not use this convention, and it is not as important as such. So don't need to be very focused or serious about this particular sign convention, because when you write the loop equations, you don't always follow this sign conventions. Okay, so this sign convention is not that important. Now this Kirchhoff law is an outcome of what? Like why does this happen? This happened because of the conservation of charge. Kirchhoff first law is due to the conservation of charge. Now you already know that conservation of charge is one of the basic property. Conservation is one of the basic charge property. So why conservation of charge? Because here you see, if 3 ampere current is coming to this junction from this line, that means there is some charge coming to this point. There's some charge coming to this junction, and this also the charge coming to the junction. And obviously, when the charges come to the junction, they won't come here and relax. Okay, they won't sit here around, so they will move on, and that is why the charge coming to the junction will be is equal to the charge leaving the junction. That's why the Kirchhoff first law is based upon the conservation of charge. Now let us move to the Kirchhoff second law. We will be doing numericals. First, let us understand the theoretical aspect, then we'll understand how to step by step do the numericals. The Kirchhoff second law, or the second law, is also called loop rule. Okay, this is called loop rule, or it is also called voltage law. Okay, this is also called voltage law. Somewhere it will be written voltage law, loop rule, as Kirchhoff first law is also called the current law. Okay, current law. Now, what is it? It is that around any closed loop of network, the algebraic sum of changes in the potential must be 0, or the algebraic sum of the EMF in any closed loop is equal to the sum of the product of the current and resistance in it. You will not be able to understand reading the definition as such. This is just a formal definition. Now you have to understand it this way. Now let's consider that you have a resistance, and this is the point A and point B. Now consider that there is a current flowing here in this direction. And this is what you have to keep in your mind always. This is how you have to think about this concept. So you always and always think as if you are walking in the circuit. Think yourself to be walking in the circuit. It makes easier. It makes the whole calculation easier, or visualization of the problem easier. So you think that you are walking in the circuit. Now, if the current is flowing I, then you would know that there will be a potential drop across this resistance. That means at this point before the resistance, there will be a higher potential, and after the resistance, there will be a lower potential. And when you are moving across like this, then in this direction, then you are moving from a higher potential to lower potential. So this will result in a potential drop. This will result in a potential drop, and potential drop is always taken as negative. Okay, potential drop is always taken as negative. There are again some books which take potential drop as positive, but you don't take it as positive. You all have to take potential drop as negative only. In the same condition, if I ask you that now that you are going to walk from this end to this end, from here to here you're going to walk, that means you're moving from the lower potential to higher potential. So this will be a potential rise. Now what was the potential rise considered in the sign? It is positive. So potential rise positive, potential drop is negative. And what is exactly the potential rise and drop has happened? That will be V is equal to IR. But in the case of potential drop, because it's negative, so I will take minus of IR. And when it is potential rise, the same thing I will take plus of IR. So practice this. I will make few practice thing here, and everybody who is watching the video, they can just pause it and practice this first. So copy these 4 diagrams in your notebook right now, and try to figure out in which cases potential drop is happening and how much it is happening, and in which cases potential rise is happening and again how much it is happening. Okay, so pause the video, draw this diagram, and then solve it, and then check your answers. So let's solve this. You are now moving from the higher potential. See, first you identify the direction of current. First you identify the direction of current. So you will see here that the direction of current is in here. That means this part will be having a higher potential. You see, look, focus here. This part will have a higher potential, and this will be lower potential because this is the direction of the current, and you are moving from the higher potential to the lower potential. So this will be what? Potential drop. You are moving from higher to lower potential. This will be potential drop. And what will be the potential drop? It will be IR, the current in this line, and the resistance, current times resistance. But this value will be taken as negative. Why? Because it is potential drop. In the second case, if you are moving in this direction, then you see, identify the direction of current. You see the direction of current is from the right to the left. That means this point definitely will have a higher potential and this will have a lower potential. And now you are moving from the lower potential to the higher potential. That means you are going to experience a potential rise. You will experience a potential rise, and potential rise is I times R, but as because it is rise, it will be plus. In the third case, you will see that you are moving in the direction of the current. You see, this is the direction of the current, and here this will be higher potential, this will be lower potential. Again, this will be higher potential, lower potential. So when you are crossing through a register, you see this is potential drop you are going to experience for all the 3 cases. So you're going to write your expression as minus of IR1, minus of IR2, minus of IR3. Okay, in this case, in the fourth case, you will see that when you are moving actually in the opposite direction to the current. So here basically will be the lower potential. Look, and here, look here, this is will be the this will be the lower potential, this will be the higher potential, again lower and higher. So when you are moving across, you will be basically potential rise. You will experience potential rise from here to here. The potential rise in this case is going to be IR1. This case is going to be IR2, and this case also is going to be IR3. Very simple, and all 3 values will be taken as positive values. Okay. Now, if you are already clear with this and you have got all these answers correct, if you have already got this correct answers, then move on to this one. Look at this diagram very carefully and draw this diagram. Pause the video, draw the diagram. We'll be solving this now. Now, let's say this is our circuit, and R1, R2, R3, R4, R5. These are the 5 resistances you can see, and you can also see the current I1, I2, I3, and I4. So let's say these are 5 different points. Okay, these are 4 different points here. And what is going to happen here? This is a junction, And here in this junction, you can see that I1 and I2 current are coming to this junction. That means at this junction, the current which is going to flow here will be I1 plus I2. Okay, will be I1 plus I2. And then again at this junction, you see these two current is again getting bifurcated into I3, I3 and I4. So from the current law, the first law, Kirchhoff current law, very easily we can figure out that I1 plus I2 is going to be equal to I3 plus I4. Okay, because that's the current which is coming to the junction, and then that is getting bifurcated into I3 and I4. So I1 plus I2 should become I3 plus I4. Now you have to walk on the circuit. As I told you before, always imagine that you are in the circuit. You are in the conducting circuit and you're walking it. It will be very easy to identify. Trust me, do like this. Mentally imagine that you are going to walk on the circuit. So here you are. Okay. I'm considering here you are. And when you started here, okay, when you started here, let the potential of this point be VA. Okay, let the potential of this point be VA. Then when you move here, it will become what? A potential drop. Now, why a potential drop? Because if you look closely, the current is flowing in this direction. And because the current is flowing in this direction, that means here there will be a higher potential, here will be lower potential. And you are basically moving from the higher potential to lower potential. Okay, higher potential to lower potential, and you will experience a potential drop. So that potential drop will become how much? The current in this resistor times the resistor, that is I2 R2, and because it is dropped, so I will take this as negative. Okay, and now you have reached where? You have reached here. Okay, after crossing this resistance, you have reached here. Okay, now you have to cross over this resistance. You have to cross over this resistance R3, and you have to cross over, and the current is flowing in this direction. So again the same thing, here there will be higher potential, here there will be lower potential, and when you cross over, you will experience a potential drop. You will experience a potential drop, and that potential drop is going to be how much? The current times the resistance. Here the current is I1 plus I2, so it will become what? I1 plus I2 times R3. Okay, I1 plus I2 times R3. Okay, and now you have reached where? You have reached this point. You have reached this point. Now if I ask you that you move to this direction, move towards here. Now when you're moving towards here, you are again going to cross the resistance R4, and the current is flowing in the same direction, I3. That means the potential drop is going to happen. There will be a higher potential here and a lower potential here. So potential drop is going to happen, and that potential drop is going to be how much? Minus of I3. Why I3? Because I3 is the current flowing in this line, times R4. Okay, and that is how you write your expressions. Okay, that is how you write the expression potential rise and potential drop with respect to a resistance. Now next we are going to understand that what happens when there is a cell. Okay, when there is a cell, what happens? Now you see the positive terminal of the cell will always be at a higher potential, the negative terminal will always be at a lower potential. So when you are crossing over a cell, when you are crossing over the cell from here to here, it will always be a potential drop. Okay, it will always be a potential drop. Now potential drop, how much of potential drop? That will be the EMF of the cell. The potential drop will be the EMF of the cell, and here you are going to take negative of E. The same thing will happen, but the sign will change when you are going to move across from the negative terminal to the positive terminal of the cell. If you do so, then you are going to experience a potential rise, because you are moving from the negative to the positive. So you'll experience a potential rise. And what will be the potential rise? The potential rise will be plus E. So minus E moving from the positive to the negative, and plus E moving from negative to the positive. Now, when you practice more complex problems around it, you will find that there are some cell that where internal resistance is also specified. Okay, There are some cell in which internal resistance is also specified, and in that case, what should you do? Now, for this, you see, when we solve the cell, when we solve this cell part, what was the direction of the current? There was no direction of the current. I did not specify any current ka direction. It doesn't matter when you are crossing over the cell. It really doesn't matter which is the direction of the current. If the direction of the current is like this, again, whenever you cross it, it will be a potential drop like this. Okay, if your direction of the current is not like this, let's say it is in this direction, then also you will cross it, it will always be minus of E. So when you are considering for the cell, the direction of the current does not matter. Whenever a cell comes, whatever be the direction of the current, when you are moving from the positive terminal to the negative terminal, it is a potential drop, whether whatever be the direction of current. And if you are moving from the negative terminal to the positive terminal, that will be a potential rise, again, whatever be the direction of current. But this is a case only when we have this a cell without an internal resistance. But most often you will get questions, a cell which is having an internal resistance. Now in the case where a cell does have an internal resistance, in that case you should know the direction of current. Without the direction of current, you will not be able to do. Let's say in this case, if this is the direction of current, okay, if this is the direction of current. Now, if this is the direction of current, that means when you are walking from this point to this point, okay, you are going to cross over the cell. So when you cross over the cell, you will come across this EMF, and this is a positive terminal, this is a negative terminal, and you will experience a potential drop. Okay, and the potential drop will be minus of E. That is the EMF of the cell. But now you have an internal resistance also, and the current is actually flowing in this direction. As we see, the current is flowing here. The current is flowing here. Now, because the current is flowing here, and this is the internal resistance, look closely, the current flowing in the internal resistance, that means there will be a potential drop here. There will be a potential drop because in the direction of the current, there will be this higher potential and this will be the lower potential. So you have to treat this internal resistance as any other resistance, as you have done before. You have to treat this internal resistance as any other resistance that you have done before. And if this is the direction of the current, from here to here, there will be a potential drop, and that potential drop will be minus of IR. Minus of IR because of the potential drop. Now, when you consider this, when you consider the same case, but the direction of the current changes, okay, the direction of the current now changes and it is from right to left. This is the current going, okay, and you are going to move from here, okay, you are going to move from here to here. So now look closely. When you are moving from here, this is the positive terminal of the cell, this is negative terminal of the cell. So this is the potential drop you are going to experience as minus of E. But now that you are going to move across the internal resistance and the current is flowing in the opposite direction, so we can see that this value will have a higher potential, this point will have a higher potential, and this point will have a lower potential. So you're going to experience a rise in the potential, and this will become rise in the potential will become plus IR. Okay, so when you are when you come across a problem which has EMF and an internal resistance is also there, then be very clear of the current direction. For EMF, for the EMF, positive negative potential rise and drop, you don't need the current direction. But when you consider the internal resistance, then you need to know the direction of current, or then only you can find out the potential rise or potential drop. Okay. So this is the theoretical understanding of the Kirchhoff law. But Kirchhoff law problem can become very complex if you are preparing for JEE advanced level questions. it can become very, very complex. And problem solving, knowing the concept is one thing, but again, solving a Kirchhoff law problem is a certain level, certain technique. As I have told you before, there are certain techniques, certain steps that you have to follow. If you follow that step in an order, you will always get a correct answer. If you don't follow that step in an order, you will never get the answer, never. And if you do one slight small mistake, the whole thing will go down. The answer nahi aayega, you won't get it, you'll get confused. So first, to go through this video 2-3 times properly. When you are very clear that you have understood, you have made notes on this, don't watch this video. This is not an entertainment video, this is an educational video. So please take your notebook, draw these diagrams, isko draw karo and do this. And when you're clear with all this thing, then watch the next video in which I will explain the techniques to solve this Kirchhoff problems.